All right, we're about to take a journey into the incredibly strange world of quantum physics. We're going to meet the fundamental building blocks of our reality. But I have to warn you, they're nothing like you'd expect.
So let me just start by asking you a question. Could a single particle, like say an electron, be in multiple places at the exact same time? Now, in our everyday world, the answer is, of course not. That's ridiculous. Your car keys are on the counter or they're not. But as you're about to see, the quantum realm, well, it plays by a completely different and much weirder set of rules.
Because when you shrink way down to the size of atoms, you enter a whole new world. And down there, the comfortable, predictable rules of our reality, they just completely break down.
Think about it like this. You throw a baseball. Its path is predictable. It's solid, right? And it's only ever in one place at any given time. But a quantum particle? Oh man, it's governed by probability, not certainty. It can act less like a solid object and more like a wave. And yeah, it can actually seem to be in many places at once.
This brings us right to the absolute heart of quantum mechanics. This concept that is so bizarre, it's like a fundamental identity crisis for the very stuff that makes up our universe. Is it a particle or is it a wave? The mind-bending answer is, somehow, it's both.
It's called wave-particle duality. And what it means is that a quantum entity isn't either a particle or a wave. It's somehow both of those things, all at the same time. Which identity it decides to show you simply depends on how you look at it.
For instance, if you set up a detector to see where an electron lands, it'll act like a nice, well-behaved little particle. It will hit a single, specific point on your detector. Boom! Just like a tiny little ball. You get one definite location. But, and this is the crazy part, if you set up an experiment to just observe its path instead, it stops acting like a ball and starts acting like a wave. It literally spreads out through space, it can interfere with itself, and it creates patterns just like ripples in a pond. And that right there is the core mystery, the same exact object having two completely different natures.
So, how is any of this possible? Well, this strange world is governed by a set of totally unbreakable laws. Let's call it the quantum rulebook. These are the fundamental principles that everything in this tiny microverse has to obey. And they really boil down to four bizarre principles that change everything we think we know about reality. We've got superposition, uncertainty, quantization, and the one that even baffled Einstein himself, entanglement.
Okay, superposition, this is the official answer to that first question I asked you. And yes, a particle absolutely can be in many places or states at once. The best analogy is a spinning coin. While it's in the air, spinning, is it heads or is it tails? It's kind of both, right? It's in a superposition of both. It's only when it lands, when you measure it, that it's forced to choose a state. Before you look, that electron really is in multiple places at the same time.
Then we have the famous uncertainty principle. Now, this isn't about us having clumsy measuring tools. This is a fundamental trade-off that's built into reality itself. The more precisely you manage to pin down a particle's location, the less you can possibly know about its momentum, where it's going and how fast. And vice versa. You can never, ever know both perfectly.
Rule number 3 is quantization. To get this one, think of our big world as a ramp, where everything feels continuous. You can have any amount of energy you want. But in the quantum world, energy is like a staircase. An electron inside an atom can only be on step 1 or step 2 or step 3, but it can never be on step 1.5. Energy and other properties only come in these discrete little packets called quanta.
And finally, entanglement. This one is so weird that Einstein famously called it spooky action at a distance. You can link two particles so that they share the exact same fate. If you measure one and find its spin up, you will instantly know its partner is spin down, even if that partner is on the other side of the galaxy. It's this mysterious connection that acts instantaneously, completely defying our normal understanding of space and time.
So, now that we kind of know the bizarre rules of this game, let's meet the players. Who are these particles that actually live by this strange quantum rulebook?
So who are these quantum characters? Well, the lineup includes some you've definitely heard of, like the electron, the photon, protons, and neutrons, and then the quarks that they're made of. And every single one of them lives its entire existence by those four bizarre rules we discovered.
Take the electron. This is not some obscure particle. Its quantum nature is the entire reason all of chemistry works. The way atoms bond together to make molecules, the way your phone works, the way life itself is structured. It all comes down to the beautifully strange, probabilistic dance of the electron.
And then you've got the photon, the particle of light itself, and a true quantum rock star. It has zero mass, and it only knows one speed, the absolute cosmic speed limit. Every single bit of light that you see is made of these ultimate speedsters, carrying the energy that powers our entire world.
So after all of that, what does this weirdness actually mean? Why does it matter? Let's try and pull it all together for the big takeaway.
Because at its very core, a quantum particle is a completely new kind of thing. You could say it's just a strange, beautiful mix of waves and probabilities and these discrete energy states. Ultimately, this means we have to just throw out our everyday intuition. The fundamental building blocks of our world are not tiny, solid balls. They're something far more mysterious, far more fluid, and honestly, way more interesting.
And that leaves us with a final, really mind-bending thought to take away with you. Everything we see, everything we touch, this entire solid-seeming universe is built from these fuzzy, probabilistic, wave-like things. So if our reality is built from this stuff, how solid is it really?